Hello and welcome to the Chapter 9 introduction video. Chapter 9 deals with the topics of molecular geometry and some bonding theories. In this chapter we'll talk about molecular shapes. In this chapter what we'll try to do is figure out how we go from something like a Lewis structure. Let's say we're looking at the Lewis structure of methane. And we've identified that methane has 4 single bonds. This chapter here is going to deal with the idea that the shape is going to center around the idea that these valence shell electrons for carbon are going to repel each other. So the electron pair repulsion model will show that the electron pairs in our molecule are going to repel each other, so the molecule will spread its electron pairs out as much as possible. So the molecule of methane ends up adopting a perfect tetrahedron geometry where all these bond angles turn out to be a perfect 109.5 degrees in the terms of their bond angles. Then we'll see a molecule like NH3 where we have a lone pair but still have 3 bonds. We have like 4 sort of pairs of electrons that are all going to repel each other. These lines, there's electrons that repel each other within these lines. So a molecule like ammonia ends up adopting a similar type geometry as methane, and it adopts also this tetrahedral type, we call it Electron-Domain geometry for all of its domains, where one of its domains is a non-bonding domain pair of electrons. In the case of methane, it takes the electron-domain geometry. We also call the molecular geometry name of something like methane to be tetrahedral. So we'll pick up that ammonia is actually called a trigonal bipyramidal, a trigonal pyramidal molecule. We'll talk about a little bit of that as we get into a discussion of the different types of shapes we encounter, as well. We'll have to see how these relate to the actual polarity of the molecule. We'll see that molecules like methane are nonpolar. Even if you make the hydrogen atom something that's more or less a negative, even if you have a molecule like CF4, what we're going to find is that there's actually no charge imbalance in a molecule like CF4, and it ends up being completely nonpolar despite having a very polar bond. So we'll have to talk a bit about polarity and why it is that some molecules that have polar bonds wind up being nonpolar in their behavior. So we'll talk about covalent bonding and orbital overlap to get into some different theories of bonding. We'll talk about hybrid orbitals and multiple bonds. And then we'll also talk about molecular orbital theory and a description of molecules in the second row of the periodic table. Things like B2, C2, N2, O2, and F2. In particular, O2 is a tricky molecule that some of these other bonding models won't be able to accurately predict some of the properties of O2. And we'll have to go to a more complicated theory to try to understand these molecules. So we'll look at MO theory, molecular orbital theory, towards the end of Chapter 9. So molecular shape is not necessarily determined based off direct inspection of a Lewis structure. For example, if you look at methane, methane turns out not to be a flat molecule like it's often depicted within a Lewis structure. The Lewis structure, though, is still helpful. It's trying to tell us how many bonds there are about the central atom in the molecule. There's 4 domains or 4 bonding domains about the carbon atom, and then none of them are non-bonding domains. Something like ammonia, similar in structure to methane, but it has 3 NH bonds and then a lone pair of electrons. The issue in these molecules are that the bonding domains contain electrons, that each of the lines in a bond represents 2 electrons. Electrons are negatively charged particles. Each of the dots on a lone pair of electrons represents electrons. These electrons are all negatively charged and repel each other accordingly. So if we have a linear molecule, then the bonding domains of the molecule are going to want to get as far away from each other as they possibly can. If we only have 2 total domains, then the way that those domains can get as far away from each other as possible would be through a linear bond with a perfectly 180-degree bond angle. Now, something like SO2 we're going to see has a lone pair of electrons on the sulfur atom. If we were counting the electrons in the molecule, we'd have 18 total electrons. So we'd have 16 of the electrons on the oxygen. Those 2 leftover electrons are the lone pair on the sulfur atom. So the electron pairs on the central atom and the bonding domains all repel each other closer towards 180-degree bond angles. Now, it's not exactly 120. We'll have to take a look a little bit more closely as we get through the chapter to see the relative repulsions of bonding pairs and electron pairs a little bit different, but we'll come back to that issue. If you look at the bonding in something like SO3, SO3 would be described as having 3 equal length bonds. You might have a double bond, 2 lone pairs, 3 lone pairs, and then the idea of residence, spreading out that double bond across the molecule such that all of the bonds are the exact same bond order, the exact same length, the exact same type. And then if all the bonds are the exact same, and there's 3 of them spread across our central atom, we have 1 domain here, 1 here, and 1 here, so 3 total domains. The furthest they can get away from each other would be 120 degrees. So if you had something like NH3 or NF3, you'd have nitrogen with a lone pair of electrons. So those electrons are going to repel the bonding pairs downward such that the molecule can adopt the same type of trigonal planar structure as SO3 adopts. So the electron pair is going to exert repulsions on the bonding domain such that we'd have 4 total domains about that particular atom. And so when that's the case, we end up adopting more of a tetrahedral-like shape, but where one of the spots is occupied by a lone pair. And these are just a few summaries of different types of structures. We're going to see a T-shaped structure emerge when we have a central atom that has 2 lone pairs of electrons. So if you're looking at a Lewis structure of ClF3, you might have drawn it like this. When you're drawing a Lewis structure, you have no real concern for the real shape of the molecule. You're just trying to figure out, okay, how many bonds do I have? Where are they? And then where are the lone pairs of electrons? We have 7 times 4, 28 electrons. 24 distributed, so we have 2 extra lone pairs on chlorine. So these lone pairs are going to repel each other. We'd have a total of 5 domains determining the structure of a molecule of ClF3, whereas the NF3 example would have 4 domains. The SO2, SO3 example is 3 total domains and just 2 for the linear case. So we'll take a bit more close of an inspection and look at these types of structures as we continue through the chapter. So what determines the shape of the molecule? Well, the bond angles and the lengths are what are really determining the shape of the molecule, like however long these bonds are, and then whatever the bond angles are, those are determining the shapes of the molecules. So we have linear shape, that's when we have 2 atoms bonded to a central atom with no lone pairs left over on that central atom. We have trigonal planar structures emerge when we have a central atom, no lone pairs, 3 bonds. We have a tetrahedral shape emerge when we have 4 domains connected to a central atom. This would be the geometry of methane. So having 4 bonding domains, all of them exactly the same, then we're going to end up with perfect tetrahedral bond angles, where all these angles are exactly the same. So we'll call these all A for angle. So the angle here would be equal to 109.5 degrees. That's the bond angle of a perfect tetrahedron. So tetrahedron gets its name from having an equal-sided pyramid with 4 pyramids on it, or 4 triangles connecting the outer atoms. Likewise, if you have 5 atoms connected to a central atom, no lone pairs in the central atom, the shape would be a trigonal plane connected with a bipyramid, axial connected set of bonds. So we have 2 atoms, 3 atoms connected on an axis, and then 3 atoms not on an axis, on like an equator around the molecule, forming the trigonal bipyramidal arrangement. And then lastly, if you had an extra atom from the last one, so if you have 6 atoms connected to a central atom, no lone pairs in the central atom, then the structure would be called octahedral. You might call it square bipyramidal, like trigonal bipyramidal. But octahedral also emerges as a name when you recognize that you have 8 quadrants of a pyramid up and down from the central atom, or from the outer atoms. So you end up with an 8-sided structure. So I always like to point out that the 8 in octahedral doesn't refer to 8 atoms attached, but rather 6, but the 8 is referring to the sides of the pyramid that emerges from that shape. Just like we had 4 sides for the tetrahedral, we end up with 8 sides to the pyramid for the octahedral geometry. So these structures are determining the shapes of these molecules. We'll see the shape plays an important role in determining some of the electronic behaviors of the molecules, such as determining some of their properties, like whether the molecule is polar or nonpolar, as a result of whether the molecule has a dipole moment or not. We'll talk about that as we get a little bit later into this particular video. Okay, so when we're looking at the shape of a molecule, what we're really trying to count are how many domains do we have. This would count as 1 domain. Even though it's a double bond, it's still just 1 bonding domain. This is another domain, and this is another domain. and then the non-bonding domain is a third. So that this counts as one domain, as do each of the single bonds. So this molecule here would have a total of 1, 2, 3 bonding domains, and then the fourth domain would be the non-bonding domain. So 4 total domains, one of them is non-bonding. So the molecule here is going to have a shape as a function of all of the domains. 4 domains can best spread themselves out in a tetrahedral arrangement. So the electron domain geometry would become the tetrahedral shape. And then we're going to try to name then the geometry that emerges of just where the actual atoms are connected. So we're going to want to come up with a name for just where the atoms actually lie. And one of the ways we can name this structure would be that it's a trigonal, but making a pyramid. So a trigonal pyramidal. And that will be the molecular geometry name. So these two domains go hand in hand. Like all the domains determine the name we assign and the shape that the overall electron domains take, and then the atoms in their arrangement gets a name based on just where the atoms happen to lie. And of course the two go hand in hand, but two different names will emerge for structures that have non-bonding pairs of electrons on their central atom. So VSEPR stands for the valence shell electron pair repulsion model, and it just says that the valence shell electrons are the ones repelling each other, trying to get out of each other's way, and exerting, if you will, their forces on each other that allow the molecules to adopt the shapes that they do. So 2 domains get as far away from each other with 180-degree bond angles. 3 domains would form with 120-degree bond angles. And then anything other than 109.5-degree bond angles would have the electron pairs too close together. They'd be closer together than 109.5 if we opt to any other type of structure other than a tetrahedral arrangement. So we're trying to minimize the repulsions that the electron pairs have with each other by getting them as far away from each other as possible. But of course we can't get rid of the domains. Like if a molecule has 4 domains, it has to spread them out somewhere throughout the molecule attached to the central atom. So 4 goes tetrahedral, 3 trigonal planar, 2 linear. So if we look here, we're just summarizing the bond angles for linear, 180, trigonal planar, 120, tetrahedral, 109.5 degrees. And you can picture the 4 sides of the pyramid, if you will, for the name tetrahedral and why that name emerges. Likewise, 5 domains, trigonal bipyramidal. So you get the trigonal shape here, all in a plane, but then a bipyramid emerges from the axial 3 set of bonds connected on the axis of the molecule. So we actually end up with bond angles of 120 on the equator and then 90 degrees on the axial to the trigonal pyramidal atom connection. So 90-degree bond angles for some of the atoms and then 120 for others. Octahedral bond angles are all 90 degrees, whether you're looking at atoms on the equator or atoms on the axis. Actually, all of the atoms are exactly the same type of connection. They're all axial atoms, so all the atoms align on an axis within the octahedral shape, unlike the trigonal bipyramidal shape, so all of the bond angles are 90 degrees. Now for molecular geometries, if we're trying to determine the geometry, what we'd want to do is start with the Lewis structure, try to come up with the best one possible. Generally, that means we are satisfying the octet rule for the central atom when we can, not necessarily expanding octets, and we are also not necessarily trying to satisfy the octet rule if it expands and maximizes formal charges. It's like for BF3, usually we're not making a double bond here. We're going to be deficient of an octet. And then for something like PO4 3-, we're okay with 4 single bonds. If we go with a double, we then would be expanding the octet. So usually we're going to stay with just the single bonds. That'll help us try to picture the right structures. We also should probably start thinking and reminding ourselves of resonance, that if we see a molecule like NO2-, which has a nitrogen double bond, single bond in its best Lewis structure with a lone pair on nitrogen, that this double bond is going to be in resonance with the other double bond such that both bond lengths are equal in length. But still in this chapter, we would still be counting this as one domain here, one domain here for 3 total domains. So we just want to kind of make sure that we can count the total domains correctly, not miss lone pairs on central atoms, because those are going to be important for determining shape. So to determine the best Lewis structure for, say, NH3, lone pair of electrons, so the shape of the molecule should take the tetrahedral shape. So we assign an electron pair to one of the spots on the tetrahedron, atoms to the others, and then we assign a name for just the atoms. And the electrons are still there, but they don't really take up much space, so we're just naming the actual geometry for the actual atoms that emerge within the structure for trigonal pyramidal. So then we can go through some of the domains and say, okay, if we have 3 total domains, all of them are bonding domains, then the molecular geometry shape is the same as the electron-domain geometry shape of trigonal planar. And if we have something like NO2- with a pair of electrons, then we'd have 2 bonding domains, 1 non-bonding domain with a pair of electrons. So we'd have to have a bent bond in this case. So the bent bond will have approximately 120-degree bond angles due to the electron pair repulsions with a lone pair. Likewise, with 4 total domains, if all 4 are bonding, then the shape of the molecule takes the electron domain geometry shape. So the shape of methane would just be tetrahedral for 4 domains, getting and spreading themselves out as best as possible. So tetrahedral for methane. For ammonia, electron pair results its repulsions on the atoms, still takes a tetrahedral electron domain geometry shape, and then the atoms are in a trigonal pyramidal shape. So a pyramid emerging with a triangular shape. So trigonal pyramidal, and then if you have 2 non-bonding domains with 2 bonding domains, that would be the case of water. So water has 2 single bonds, 2 pairs of electrons. So that should take also the tetrahedral shape, electron pairs in 2 of the spots, and then bonding domains on the other. So the bond here would be predicted to have a bond angle of about 109.5 degrees. Now if you go down further, if you say, well, what about 1 bonding domain, 3 non-bonding domains? That would just be a diatomic molecule. So once you get down to having just 1 bonding domain, that's just a simple diatomic molecule. And of course, a diatomic molecule, just 2 atoms connected together, of course, it'd have to be like a linear connection. So we stop with 2 bonding domains for our structures, can't go any smaller. We need at least 3 atoms to start talking about the geometry of the molecule. If we have 2 atoms, we already know the shape. So let's talk about the non-bonding pairs and bond angles for a minute. So non-bonding pairs are physically larger, they're like more spread out. So you take your charges on your atom, on your nuclei, you put 2 electrons in the middle that are bringing those nuclei together. You're spreading these electron pairs a fair bit out compared to having a non-bonding pair of electrons, where those negative electrons are going to be closer in on the nucleus due to not having another nucleus stretching them out further away from the nucleus. So you end up with a more compact, closer to the nucleus, and then like a wider electron pair for a non-bonding domain. So your repulsions are going to be greater with this electron pair here because it's closer to the nucleus, making for like a wider orbital, so the atoms contract downward. And another good reason why that is because the electron pairs in the bonding domains are spreading out to a greater distance. So like the nucleus of hydrogen is pulling and stretching out that bonding domain compared to the non-bonding domain. So instead of having what we'd expect to be 109.5 degree bond angles, they end up closer to 107. So likewise, if you have 2 pairs of electrons, the problem's even worse. The atoms are going to get even a little bit closer together, but not that close. It's only a couple degrees off of perfect tetrahedral 109.5 degrees. So water's bond angles a little bit less than NH3 and less than CH4. CH4 is perfect 109.5 degree bond angles all the way around the molecule, because there's no way any of the 1 bonds is somehow exerting a greater force on the other bonds, so all the bonds are perfectly 109.5 degrees in methane. What about having a double bond? So if we have a double bond in something like, this is actually phosgene, a nerve agent, but if you have a double bond here, you have 4 electron pairs, they're going to exert a greater repulsion on these longer single bonds. So double bonds generally shorter than single. We also have more electron pairs thrown into the bond, so the repulsions are going to be greater So the chlorine atoms are going to be squeezed together for an angle less than 120. And then the angles here greater than 120 degrees. Now it's still planar. There's still no way or no reason why the molecule would adopt a structure out of planarity. So it's still a planar molecule, meaning all the atoms exist within one plane. If you picture a similar molecule of, in terms of structure to phosgene, perhaps SO3 sulfur trioxide. So SO3, you might go with the Lewis structure with a double bond, 2 singles, negatively charged oxygens, 2 plus sulfur. Now the key would be that you have resonance actually stabilizing, or not stabilizing, you have resonance spreading out this extra double bond over to here, and another Lewis structure where you're down to a single here, and then you have another Lewis structure, you end up with your double bond over here and single over here. So the real molecule will spread out that double bond at all times across all of those 3 bonds, such that all of these bonds have an order of about 4/3. You have about 4 bonds being spread across the 3 actual connections of atoms. And so all the bonds here should be the same length, the same type, the same order, so they exert the same repulsions on each other. So the bond angles here actually end up being still perfectly 120 degrees. So still 120 degree bond angles in SO3. So it looks like it would be like the phosgene example, but phosgene has what we call a localized bond, a bond that's localized between the C and the O. So we get a double bond that's always there and never spread across the molecule. In the case of SO3 2-, if we go back to, or not SO3 2-, SO3, this double bond here is being spread across the other connections at all times, such that all the bonds are actually exactly the same. So we have to apply a little bit more thought to something like SO3 to see that the bond angles would actually be all exactly the same. So then if we look at trigonal bipyramidal domain, this is characterized as having atoms connected on an axis. So these would be the axial atoms in this geometry, and then the positions on the equator of the molecule would be the equatorial atoms within this geometry. So you end up with 90 degree bond angles for the axial to equatorial atoms, then the equatorial atoms have 120 degree bond angles. So now this is going to play a role in determining, like, if we're replacing one of these spots with a lone pair, do we choose this atom or this atom, because those are 2 fundamentally different positions within the molecule. So let's take a look at the geometries we get within the trigonal bipyramidal domain. So if all 5 of the domains are bonding, like in the case of PCl5, we have 5 single bonds, no lone pairs on phosphorus. Then of course our molecular geometry also would be trigonal bipyramidal. And then if we lose one of the domains to a bonding pair, so you have a bonding, non-bonding pair of electrons, which domain are we going to choose? So you have 2 choices on the trigonal bipyramidal. Are we going to choose one of the axial position atoms to replace with a lone pair of electrons, or one of the equatorial positions? And you can see from the figure that it's the equatorial position that gets chosen to be the position of the lone pair electrons. So you have sulfur, lone pair, 2 fluorines opposite each other on an axis, then an F and another F on the equator with a bond angle of about 120 degrees. Now what you can conclude here is that that must have been more stable than the alternative, which would have been losing an axial position and replacing that with the electron pair. And so here you can imagine that this must have led to greater repulsions than in the case of the equatorial position. So we actually had 3 90-degree interactions if we had chosen the axial position, but only 2 in the better arrangement that was actually chosen by the molecule. So we get 2 90-degree interactions in the case of this seesaw geometry. So if you take the structure of something like SF4, you can actually have like an F, S, F, linear connection, fluoride, fluoride, lone pair. And this looks like a teeter-totter or a seesaw. So that's why the molecular geometry name for 4 bonding domains but 1 non-bonding domain is seesaw in the molecular geometry name. Now SF4, 4 bonding domains, not tetrahedral. Tetrahedral has to have 0 non-bonding domains. Here we have 1 non-bonding domain. So in the case of having two non-bonding domains, two pairs of electrons, and three bonding domains, that's the case for something like ClF3. So when we're doing the Lewis structure for ClF3, that's 28 valence electrons. So if you do your central chlorine, 3 fluorines, then what we end up with is lone pairs on the fluorines. That's 24 total electrons. And then you have 2 left over. Well, those go on chlorine. So we have 2 electron pairs that are going to take the 2 equatorial positions, because we certainly would not want 2 electron pairs to be 90 degrees relative to each other. That would probably be the worst consideration. But we also turn out not to want them to be 180 degrees relative to each other, because then they would have a bunch of 90-degree interactions. So this geometry here, it's the T-shaped geometry, minimizes the repulsions of the bond pairs and the electron pairs. And the structure, if you were to turn it on its side, looks like the letter T. So this is the T-shaped molecular geometry. So for the molecular geometry, you're trying to come up with some sort of a name for the geometry of just the atoms within the structure. Of course, those geometries depend on the total domains being 5. So the electron-domain geometry is still electron-domain geometry of trigonal bipyramidal, but the molecular geometry name for ClF3 would be T-shaped. Now finally, when we have xenon F2 has 3 pairs of electrons on the central xenon atom, and so then those are going to take the positions on the equator, on the equatorial position of the atom, and then the fluorines will be on the axial position, opposite each other. So in the case of 2 bonding domains, 3 non-bonding domains, and we have a simple linear atom. So whenever you have a molecule that has 3 atoms connected together, the geometry name should either be linear if you have a perfect 180-degree bond angle, or bent if you have some type of bent bond where it's not 180 degrees, like in the case of water or NO2-. Those are both bent. Okay, so now let's go through the octahedral domain. So the octahedral domain, all 6 of those domains, if they're bonding, then the molecular geometry would be octahedral, just like the electron domain geometry. So that's the case for something like SF6. And so then, I think that's an extra letter. So if we have 1 non-bonding domain and 5 bonding domains, that's still a total of 6, so still within the octahedral domain. Now you can replace any one of the positions on the octahedral geometry with an electron pair, and you arrive at the exact same structure. You have a square and then a single pyramid. So you get a square pyramidal geometry, not square bipyramidal. Square bipyramidal would be 2 pyramids. We only get 1 pyramid from the square plane in the central part of the ring of this molecule. So square pyramidal would be the name for something like BRF5, 5 bonding domains, 1 non-bonding, and then 4 total bonding domains, 2 total non-bonding domains for 6 overall, still octahedral. And then the 2 options would be 90 degrees relative to each other or 180. And 180 sounds like it's going to reduce those strong electron-electron repulsions the best. So we put an electron pair opposite each other, and then we have 2 sets of fluorine atoms on an axis together. So that would be the structure for something like xenon F4. So something to point out here is xenon will form compounds. It's the largest, one of the largest of the noble gases. Radon is a bit trickier to work with since it's radioactive. So xenon is the largest of the non-radioactive transition, largest of the non-radioactive noble gases, and it can form some compounds. Now, why would xenon form compounds? Well, of the noble gases that you want to work with, it would have the lowest ionization energy, so it's the easiest to ionize, and so it's the easiest to pair up with something like fluorine. Now, it's not stable. Like, you can't form xenon F4. We saw xenon F2 in a previous example. Like, you're not going to make these compounds and put them in a bottle, but you can make these at low temperatures. They could exist so that you can characterize the molecules, and if you warm them up, they end up decomposing back to xenon and F2. So not the most stable of compounds, but they still exist long enough so that you can characterize them at least at low temperatures. Now let's take a look at the shapes of some larger molecules. So the first example here is CH3COOH. So notice that we have carbon double bonded to an oxygen, single bonded to an oxygen to an H. So we'd have lone pairs on the oxygens. because oxygen, like we pointed out in chapter 8, tends to form bonds with other atoms such that it has 2 bonds and 2 lone pairs. Carbon tends to form 4 bonds. We have 1, 2, 3, 4 about the carbon that I've circled. And then the carbon here is the CH3 bonded to a carbon. We also have 4 bonds there. So what we're looking at here is just the simple geometry of something like acetic acid. So if you get a structure that looks like this, then you can easily put together a Lewis structure. With the idea of get 2 bonds, 2 lone pairs to each of the O's, 4 bonds to each of the carbons. You can even come up with something like CH3NH2 pretty quickly just by going CH3. Now it's just a single bond to the N because that gives carbon 4 bonds. Hydrogen likes 3 bonds in a lone pair. And so we get that pretty quickly and pretty easy to write for something like CH3N2. Now let's talk about polarity. Polarity is pretty tricky, but it's pretty important because CO2 ends up being nonpolar, and as a result, it doesn't have as strong an affinity for itself. It's harder for it to stick together, if you will, so it's going to have a lower boiling point and melting point than compounds that are polar. So water is a similar compound that actually ends up being polar. Now, what goes on here is that the 2 oxygens in CO2 are polarized. They have a greater electronegativity than carbon, so they're pulling electrons in the bonding domain closer towards the O atoms. Carbon's picking up a formal positive charge as a result. But the issue here is you get this big partial negative charge, partial negative. So if you park a second CO2 molecule, so if you have a second molecule of CO2, then you're just getting repulsion, not attraction for the molecule. So for 2 adjacent CO2 molecules to become attracted, what they're going to have to do is somehow induce a molecular dipole moment in each other in order for the 2 molecules to be attracted. There's not like a built-in polarity in the molecule to allow 2 adjacent molecules to be attracted together. And so what results is a weaker intermolecular attraction between adjacent CO2 molecules, and it's easier to separate them. So what ends up happening is that the boiling point and the melting point of a compound like CO2 ends up being lower than you would expect for a similar but polar compound. So water is situated in such a way that you get a negative charge on one end of the molecule and a big positive charge on the opposite end. So on this side of the molecule you get a big positive charge, and on this end you get a big negative charge. So you can take a water molecule and stack them on top of each other and have the plus and minus built-in electrostatic attraction. So when you get electrostatic attraction, you can kind of think, okay, in terms of the molecule, do we have a net pole? Do we have a net dipole moment? Well, we do. We have a dipole moment that points towards the negative charge, and you can imagine stacking dipoles or stacking molecules, and they're going to be more attracted when they have these built-in charges in polar compounds. So CO2 and water both contain polar bonds, but only water is a polar molecule. And it has all to do with the geometry and the fact that water is bent and not linear like CO2. So CO2 being linear allows the 2 dipoles that are pulling away from each other to cancel each other out. So there's no net pole, there's no net dipole moment in the molecule. Another way I like to think of this is if you were to have a molecule of CO2 in the middle of 2 plates. So let me do a little erasing here for a second. So let me erase this. So if I'm going to put a positive charge over here and a negative charge over here, where's the molecule going? Is it going to fly towards the positive charge or the negative charge? And you may say at first, well, wouldn't the negative charge repel the positive charge? And it might, but it's going to be in such a way the molecule is just going to end up spinning in this electric field. It's not going to experience a net pull towards the positive direction of that field. The one negative charge might, but then the other negative charge is going to see that it's attracted, and the molecule is just going to end up being in a spinning motion. Whereas if water is put a positive charge and a negative plate on water, then the negative charge on water is going to be more attracted to the positive direction of the field, and it will travel towards that plate. And so you can imagine that 2 adjacent molecules are just kind of following the same idea, that if there's this built-in charge separation in the molecule such that you get a big negative charge on one side, a big positive charge on the opposite side, then 2 adjacent molecules can be more attracted together, have stronger attraction as a result. So that will lead to an increase in the boiling point and the melting point that you might expect for a molecule that didn't have that type of polarity built into it. Okay, now before getting into valence bond theory, I will say predicting dipole moments, we'll have to go through a lot of examples in lecture so we can look at different types of molecules, so we can start to predict which molecules should or should not have dipole moments. We'll get into the properties of liquids as we get into chapter 11 later in the course. So valence bond theory has to do with the overlapping of orbitals to make bonds. So if you imagine two electrons in a 1s orbital, that these electrons can overlap here, bring the nuclei together as you get the negative electrons of each of the atoms attracting to the opposite nuclei and pulling together these orbitals in such a way and seeing this overlap. The overlapping of orbitals is one type of bonding theory for why bonds exist. So if you take like a 3p orbital, the largest orbital of chlorine, and then the 1s, the valence orbital of hydrogen, you can get overlap here in terms of overlapping of orbitals. So you can also get overlapping of the largest orbitals in two adjacent chlorine atoms. So you can look at chlorine and say this could be like a 3p valence bond orbital, or you could have a 1s 3p orbital in something like HCl. So it gives us an idea that overlapping orbitals could be the origin of bonding, so that the electrons can be spreading out their spinning motions into the neighboring atom. And so another notion that will get picked up in molecular orbital theory a little bit later in the chapter that we'll talk about in the next video, in the second half of chapter 9, will be that each of the, that you almost get like a new orbital when orbitals mix together. You're actually going to get two orbitals in MO theory. So if you take two orbitals in MO theory, you'll get a stable bonding orbital that can hold two electrons, and you get an unstable or a less stable antibonding orbital that can hold a max of 2 electrons. Okay, and so you get this idea that just like atomic orbitals can hold 2 electrons, molecular orbitals as well can hold 2 electrons each. And so we'll be picking up more of those ideas as we get into MO theory in the second half of the chapter. So valence bond theory also helps us understand that you can't just keep compressing a bond. So you can imagine taking the positive nuclei, each of the electrons on an H atom, bringing them together. So at far separation, the atoms have a relatively high energy. And so if we keep separating the atoms, have one H here, one H further away, that the energy is plateaued and it's no longer increasing anymore, so it's plateauing at 0. But bring the atoms together, the energy drops as we're making the bond. So you get the maximum overlap between the hydrogens at about 0.74 angstrom. If you keep pushing the atoms together, what happens is your like charges start to repel. So the 2 nuclei begin to repel each other, and then the 2 electrons begin to repel each other. So you get nuclear repulsions. You also get electron repulsions when you keep contracting the atom beyond its ideal or optimal bond distance. And so then, of course, we learned back in chapter 7 that as the atom sizes grow larger, then the bond lengths grow larger as well. So you can get some bond length trends as they relate to the size of atoms with our understood left to right trends following chapter 7. So from valence bond theory, orbitals can overlap, and then when orbitals do overlap, their electrons are being attracted to the neighboring nuclei, and that's a net stabilizing effect, and the energy drops. So we get the potential energy dropping in the case of making bonds, and then if you have your bond made, you have H2 made here at its optimal bond distance of about 0.74 angstrom, that it costs energy to then break the bond. So if you want to go back to having 2 separated H atoms, then you have to have energy absorbed by the bond in order to have it then broken. All right, well, that's the first half of chapter 9. I don't think we did a lot of examples here today on dipole moments, so we'll look at some more examples of predicting which molecule should or should not have dipole moments in lecture for this material, and we'll move into talking about molecular orbitals and molecular orbital theory in the second half of chapter 9 next time. All right, thank you for the attention. See you in class.